having a wonderful day today. I'd like to start out by, again, thanking Weibold, also EcoGreen and our management team there. A lot of effort goes into putting these on, and we appreciate everybody's efforts in that. As Augustina pointed out, my original background is in plastics. Why do we do micronized rubber and plastics? Well, when I got into the wonderful world of tire recycling in 2006, was when I first was introduced to this industry. It was still pretty much kind of in its infancy, and we were looking for products, or I should say materials that we could introduce into different things. Obviously, tire dried fuels and chrome rubber and infill and things like that. Rubber mulch were very popular. By 2009, after 3 years in the industry, I realized that we needed more opportunities to find other materials. So I kind of went back to my plastic roots and went back to my friends that do compounding and asked if we could start introducing micronized rubber into the plastic compounding industry as a way to try to make newer materials similar to TPEs, thermopolyethylenes, and TPOs, thermopolyolefins. We had a lot of success early on, and since I would say 2011, 2012, this has become a very, I shouldn't say very common, a fairly common material that's used within the Midwest and some parts of Europe. So I hope you enjoy the presentation that we prepared, and I look forward to your questions at the end. So micronized tire rubber use in plastics. How do we do that? Well, starting with why do we do that? When you look at the market, this is from the Scrap Tire News market analysis. The last one that I have is from 2019. And I would just point out that in the bottom right-hand column of that chart, you can see how much rubber is used in what it says plastic blends, 20 million pounds annually as of 2019. And when you compare that to more common uses like asphalt, molded products from chrome rubber and urethanes, it's obviously a very small percentage. The percentages are coming up year after year, and we're encouraged by that. But I think we still have a lot of opportunity and where we can grow these markets. So for those that are familiar with tire processing, the first section may be a little bit of a redundancy, but I think it's important to go through this process because one of the critical factors in doing or adding the micronized rubber is to make sure that it's A, micronized, very small, and B, just as importantly, that it's very clean. Obviously, plastics industry guys that they have very expensive machinery. Their screws are very expensive that process the materials, and they certainly do not want any metal, rocks, other foreign debris in the material. So the processing of the rubber itself is very critical to the overall success of this. And I want to briefly run through these are the four primary steps that whether it would be EcoGreen equipment or other tire process manufacturers equipment, the processes are still pretty much the same from one to the next. So starting with the shredding process, um, disposed tires are collected and sent to a processor. Here you see an example of a processing line that EcoGreen's installed. And what we're doing is we're breaking that initial material, the whole tire, down into what we call a chip. The standard chip size would be 4 inches, but you can use other sizes. If you look on this particular photo, just to the left of where the shredder is, where the second conveyor comes out, we achieve that chip size by way of a disc wheel classifier. You could also use a vibratory screener. But the point is you're going to tear that whole tire apart, generally through a 2-shaft shredder such as this. And you're going to tear it into a 4 to 6-inch, 8-inch chip. And then that material is going to go on to the next process. The next process is called rasping or a grater. We also call these machines liberators because they liberate the wire from the rubber material. During this process, again, this one you have an internal screen, and you can vary the size of the holes on the screen. When you get down below an inch, you start to really clean the wire from the rubber, and you also get very clean wire. That wire can also be recycled. The wire is cleaner by the smaller screen size you go. So in the processes where we're making micronized rubber, what we like to do is run at least a 3/4 inch are no bigger than a 3/4 inch screen size. 5/8 is optimal because you're getting the rubber reduced to the smallest size you can while also getting the wire as clean as you can. In this process, the first two, I should say, both the shredder and the grater process, you're using high torque, low speed machines, and you're not really creating a lot of dust. These first two are basically reducing the material from whole tire small enough and getting the wire out. That's the concentration of the first two steps. So the materials produced through the shredding and rasper process, you're going to get obviously the tire shred, the smaller rubber. You're going to get the, oops, I just noticed we have a backwards there on the nylon and the wire. The one on the bottom left is actually the wire. The other one is the nylon. And then you're going to go to the granulator. So when we go to the granulator process, this, for those that may be involved in plastics now, these machines are very similar to your standard plastics granulators, and they're going to reduce that 5/8 rubber nugget, the bigger pieces, down to a very small crumb size. And this is where we're really liberating a lot of the nylon. The nylon material is a nylon 6. There are uses for it. They will use that material. Oh, and for instance, in oil absorption booms, they'll stuff it into like a synthetic sock and use it for booms. And they also use it for tire-derived fuel material that can go into kilns or municipal solid waste incinerators. So at this point is where we're really liberating the wire or the nylon, and we're also reducing the material in size again from 5/8 down to about 1/8 inch minus. From that, we go to a what we call a crumb buster. These are typically referred to as cracker mills. The cracker mills are uh, basically two giant rollers that are corrugated. They're grinding against each other. One's spinning fast, one is spinning slow. And at that point, we're reducing that crumb rubber down to what we call the micronized rubber. We found through extensive testing that the smaller you go, the better the rubber seems to interact with the plastics materials up to a certain point. And what I mean by that is if you're using 30, 40 mesh down to about 80 mesh, that's a size material that the plastics processors are used to using. You can micronize rubber specifically through like cryogenic grinding, where you can get all the way down to say 300 mesh, very very small material, uh, which although that would be absorbed well by the plastics, number one, it becomes very expensive to make that size, and number two, it's very hard for the plastics processors to use those materials because they're not used to using, in most cases, materials that are that small. So we like to focus on 30 to 50 mesh, which our specific cracker mill is able to produce in very high quantity, and it works very well in the mixing process for the plastics processors. So this is the point where we've got a nice clean micronized rubber, and we're able to take that material and then put it into the plastics processing stage. So I have to ask just for a second here if Augustina, this is coming up very small on my slide. I need to increase it a little bit. Is there a way we can do that? Let's see
You
here.
can maybe
Yeah,
click to,
I'm fixing
to
it.
zoom in.
Yep, there we go. So hopefully everybody can see this a little better. I think that was a little small before. I apologize. Okay, so making plastic rubber. I think we jumped ahead there. There we go. Apologize for that. So, how is micronized rubber used in plastics? Well, the micronized rubber can be introduced in the plastics process either as in the initial production phase or into the plastic pellet phase, which is where we're compounding an extruder. And what I mean by that is if you're introducing it into the uh, say just into an injection molder or a blow molding machine, you can mix it into the mixing stations that they have at the machines, and they can do that more as a filler. So generally, you're doing it at up to about 10%, and basically what you're doing there is you're offsetting the cost of the plastics. So a good example would be back when I was in the plastics industry in the 90s. Plastics prices did what they're doing now because they kind of follow oil, and they would go up very high in cost, and people would look for ways to offset plastic cost. So, for instance, the company I was working for at the time, we were doing large blow molded construction barrels for highway construction zones that would weigh about 30 pounds. By introducing the material talc, they were able to lower their cost by taking, the cost of plastics at say 90 cents a pound and replacing it with talc at 5 cents a pound. So even though they were only doing this at 5 to 10%, the cost variation between the talc and the plastic made that very advantageous, even though they might only be saving a few pounds per part, but they're making millions of parts. So it has a huge impact. Want to try to page down here a little bit on this, and it's not letting me, so let me reduce this in size a little bit. So try to read this a little better here. Hopefully everybody can see this. But adding the rubber at the machine will most likely require customization of the machine in some ways, and or the addition of specialized blenders to mix the rubber and plastic at the machine. So again, what I'm saying is if you're taking the raw rubber and trying to introduce it at the machine, you're either going to have to change your screw configuration in that injection molding or blow molding machine to get a better mix of the material, or more than likely you're going to mix the material very well in like a volumetric or a waste scale blender, which is mixing the additives, the plastic, the rubber, all at one time into the screw. So it usually requires some tweaking of the process. When you compound the materials beforehand, and we'll get into that in a minute how that's done, what you're doing is you're eliminating the need for the plastics processor to have to do that. They don't need any fancy mixing equipment. Everything's coming in packaged very nicely into that pellet. And again, you can do not just the rubber, but you can do other additives. You can add additives for color. You can add additives for smell. You can add additives to make the plastic and rubber play nice together. So it's really the compounding, the technology of the twin screw compounding that we're going to talk about is really where we're able to take the rubber material and transform it from just an additive as a filler to a specific type of plastic rubber pellet that is very easy for the end use plastics processor to use. So both, as I mentioned earlier, both ambient and cryogenic materials can be used for this process, but there's a significant difference in terms of cost, as I mentioned, in terms of size. And we've found through extensive third-party testing that when you use ambient ground material, which is what you get from a cracker mill, such as our crumb buster, the material comes out like a snowflake. So it's flat and it's more like a snowflake and it has lots of surface area. When you're cryogenically grinding the material, you're basically getting a sphere. So what we found is that the olefins, let me back up a second. The rubber material, of course, is vulcanized, meaning it will not melt. It's going to melt basically at 425, and then it's going to char at 426, so or catch fire. So you basically want to look for olefins, polypropylenes, polyethylenes, materials that process at or below 400 degrees. And then what's happening is as you're running that rubber particle down through the screw, it's warming up, it's heating up, it's softening the edges, and it's allowing the olefins from the polypropylenes, polyethylenes to help link the materials. So that's really what we're doing. We're never really melting the vulcanized material. We're just using the material as kind of a hybrid filler that does absorb the oils from the olefins and allows the material to play nice with the plastics. So again, we believe that the ambient ground material is a much better material because it's truly locking together with the olefins, whereas the cryogenic materials are just touching at certain points. So plastic processes where micronized rubber can be directly introduced. There are a few as we talked about. Sorry about that. A few as we talked about, such as injection molding, blow molding, um, gas assist molding. The other additives that can be added to enhance, again, can be things like UV protection. You have fire retardants, colorants, different things of that nature. Then we have when you have compounded blends that are above 50%, These are things that are becoming more like a thermopolyolefin or a thermopolyethylene. And where this is important is that those materials typically cost, and I'm talking about materials that are similar to, say, Santoprene, for those that know plastics, very expensive materials that run $2, $3 or more a pound. And while those are very specific engineered grade natural rubber plastic blends that might work for, say, an air hose or an air boot within an underhood car application, you also like that type of material for other things. For instance, that type of material would make an excellent mud flap on a truck, but you wouldn't use a 3 pound per $3 per pound material to make a mud flap. So if you can make a similar material uh, out of the plastic rubber compounds and get that below $1 a pound, which we've seen achieved, it becomes a very attractive cost and a very attractive material to use for those types of applications. Twin screw extruders are the ones that are best used for compounding. They take the plastic and the rubber and run them through a series of different screw designs within the extruder. Some that are created to do mixing, some that are created to do pressure. Some parts of the screw are kind of neutral, where the material just kind of hangs in for a minute and allows the volatiles to expand off of the screw. So there's a lot of technology that grows into screw design. We could do a whole presentation just on screw design. The important thing to know is that the best way to mix these materials is with a twin screw extruder, because that's what those types of extruders are made for. So what is a twin screw extruder? Hopefully we can see this here. See if I can make this again. Apologize that the sizes here aren't quite right. So basically, what we're talking about on a twin screw extruder is we're going to take the material from the tires, the recycled plastics or virgin plastics. We're going to add everything into a mixer. You're going to see a video of this in just a minute, and then we're going to run it through the extruder, and the offtake will be either plastic rubber pellets, or it can be sheet, or it can be extruded profiles. But the idea is, by the time it comes out the end, it is a completely new material than what it went in as. So there's a view of kind of what a typical extruder would look like. If it came from us, it would be, of course, our lovely eco green color, but we could paint it whatever color you like. And then you see on the right the pellets. The next thing I'm going to show you here is just a short video. Short video of the uh, process that we put together with a compounder we worked with. So let me pull this up, and hopefully everybody can see this video very good. Hello, Augustine. We're
Yes,
having problems. What is the issue with the video?
you should be able to click on the bottom to play.
Yeah, and it is not letting me. This worked great in testing.
Yeah, indeed.
It says stop video, video settings. Whoop, sorry, that's not it. Augustine.
I
Uh,
still cannot see the video. We see the slide, but it's black. So
okay,
unfortunately, I cannot control it here.
I
Otherwise,
can't. Yeah. All right. Apologize on this. Basically, what that video was going to show is that we're able to take, again, in that particular video, what you would have seen is the plastic pellets coming in from one angle into the mixer, the plastic recycled material, I should say, it's a flake. You would see some additives dropping in, and then you would also see the crumb rubber coming in. It goes through an extruder, as I say, as the twin through extruder, and it's able to come out the other end as a pellet. And then what we would have shown in that same video is those pellets then we took to an injection molder in Michigan, and we were able to manufacture from that material handles for tin snips. They were able to put it directly into the machine. No changes in temperatures, no changes in their processing techniques at all. It was simply replacing the all plastic pellet that they had with a new plastic rubber pellet, and we were able to run that material. So where, again, we'll go back to where can you use the materials that are in pre-compounded forms, such as we're talking about now, well, the ones that we've done extensively, the processes that we've done extensively, and that we're going to show you some photos of parts from here, we're done in injection molding, which is where you're basically taking the pellet, running it in through a hot extruder into a mold that's closed, injection the mold, open the mold, out comes the part. We're doing it in blow molding. In blow molding, as you'll see in the video or a slide, we're going to run the material through an extruder, extrude what's called a parison, which is kind of a molten tube of plastic, then close the mold, blow up the part. In gas assist molding, very similar to injection molding, where we're going to run the material through a screw into a closed mold. In gas assist, we're actually putting either nitrogen gas into the screw, or we're adding what's called a foaming agent into the screw, which makes the plastic swell up. So this is a type of molding where they're doing very large parts, such as skids or tubs, like animal watering tubs, cattle troughs, and they're able to make very large parts, but with little tiny air bubbles in it to help lighten the overall part. And then profile extrusions is another one. And here, what we're talking about is things like sheet, where we're able to then cut the things such as mud flaps or certain sheet sizes out of that. So we'll start first with injection molding. Again, on injection molding, what we're doing is we're with the plastic pellet, and hopefully you can all see my little cursor here. We're putting it right in here in the hopper, the plastic granules, and with these materials, you're able to go directly in there. Now you may have to, or this is a good thing, you may have to adjust your temperatures, but you would be adjusting them down. And a good example is we had a client that was manufacturing a specific part at about 365 degrees Fahrenheit, and when with the all plastic material, and when they used our 50/50 rubber plastic blend, they were actually able to process at about 320, about 45 degrees less, which is significant. And of course, the question comes up, well, why is that? And what we believe is happening is because of the rubber and the fact the rubber is not melting, it's actually creating friction within the barrel as it's going down, creating friction, which creates heat. So the higher the rubber content, the more likely you are to be able to reduce your temperature, your operating temperature within the molding process. And that's not just specific to injection molding, that also transfers to blow molding, to the extrusion process, and also for like single screw extrusion where they're doing sheet. So again, important to note that there is a change that may need to be made in the processing system that you're using, injection, blow, whatever. But the point is, it's a good change because you're able to lower your screw temperatures, which thereby saves heat. If you're running 300 and some degrees and you're able to lower it by 30%, that means you're 10% less heating elements required. So again, a good thing. Excuse me here. So that's the injection molding. When we look at blow molding, again, very similar in that you have an extruder up top. Again, in this system, we're putting the pellets right into the hopper. There's no need for any special blending. We're running it down the screw. We're filling in blow molding. This is called the extrusion head. This is the head of the machine, and this is filling up, and then squeezing it out is where it's coming out of the parison. And then the parison comes down. They close the mold. They inject air either in this case it's a bottle, or if it was say a shed roof or um, some other type of part that you could put a hole right in the side, they might inject air through the side and blow that parison up. So now everything's under pressure, a couple hundred, maybe 100 to 200 pounds air pressure, and it sets in there for a minute or two while the tool is cooling all around it, and then they open it up and out comes the blow molded part. Again, the key here is we're introducing just a pellet. We're not having to do a lot of special blending to get the material in. Gas assist, very similar to the injection molding. Again, they're using this type of technology primarily for pallets and very large parts. The nice thing about the gas assist when we use the material in that is gas assist have multiple heads. So it's hard to see it in this photo. But unlike an injection molding machine, and let me just page back to that real quick. Here you see we have a single injector, what they would call a sprue. Now you could move this off and have a few different gates or sprues into this, but typically it's a single injection unit, this being the injection unit. On the gas assist, it's hard to see it, but you have the injection unit here, but then you have a bunch of little smaller injection units all positioned across the part. So on a pallet, a 4x4 pallet, you may have as many as 20, or not 20, 16 different injection units that are putting plastics into this part. That's important because, again, with the rubber in there, the rubber isn't totally melted. So the quicker you can get the material into the part, the better surface finish you're going to get. And there are other things you can do to improve surface finish post injection, and we'll talk about that in a minute. But the bottom line is the quicker you can get the material into the part, the better part you're going to get. So, what are some examples of parts that are made with micronized rubber that are added during the process? Not a pre-pellet, but it can be mixed right in. Well, here's a couple parts that I worked with. The one on the left is from a gas injection company. These were water tanks used for cattle feeding or cattle watering, small goats, pigs, cattle, etc. And in this process, they're able to introduce up to 15% micronized rubber, not in pellet form, but just direct rubber. And the reason for that is A, it's a small percentage, but B, and most importantly, in the gas assist, remember that we're also introducing nitrogen and we're introducing or nitrogen or a foaming agent. And we're also introducing the material into a screw design. Gas injection machines are typically meant to run very high quantities of recycled material. So, unlike an injection molding machine that's operating with a specific design to create very high pressures of, say, 28,000 pounds to put that material into the mold and really pack it in, a gas machine might only operate at 5 or 6,000 pounds because it has a type of screw that is similar to the twin screw design and is creating a lot of mixing activity because again in gas injection there's a lot of recycled material, there's a lot of additives that they're putting in there that are trying to get that material to mix real good. So the screw designs are a little different, the pressures are a little different, and because of that they're able to add some material direct in. If you were to use the pellet and do the same thing, they could probably get that up to 50 or 60% rubber in that same part, but then it might be too flexible for what they want to do. So in this case, it works good to just introduce it directly at the machine, but if they wanted to get higher quantities, they certainly could. The part on the right is an extruded sheet with 20% micronized rubber. Again, this is rubber going directly into the extruder, but it's a mixing extruder. In this case, it was a single screw extruder, but it was used for doing recycled materials. So it had a special section of the screw that, like a twin screw machine, would create very good mixing within that small segment. And because this was just being produced as a sheet to then die cut out mud flaps for semi trucks, it worked very well. But again, very uncommon to be able to introduce that directly in. So what are the types of parts that we can make when we use the pellets? All of these parts that you see here were used with 50% rubber, 50% plastic, and to show going from the left, that is it's an equestrian jumping branch. So if you have horses and they're jumping over a pole and they want to simulate branches on top of that pole that they can hear the horses hit, that's what that is. On the very bottom, there's a screw. It screws into the pole. The roof vent obviously speaks for itself. It's a roof vent. The parts on the right, the mop bucket and the trash bin, both 50% blends. We're able to take those pellets and you can tell from that large trash can that that's a big part. That's a 50-gallon trash can, and we were able through a single sprue, I should say, we were able to injection mold that very large part and create a very nice looking part as well. And then the last one on the right is a truck step cover. So along where you jump and get into your truck, that would be the rubber pad that goes on top of the metal truck step. Blow molding. Here's a few examples of blow molding. We have a kayak seat on the left, an air duct in the middle, and a small soap bottle on the right. The interesting thing about blow molding with this material is in blow molding, they're used to using a lot of recycled content. But the challenge with that is, again, if I go back to the blow molding process, where this parison comes out, the what they call parison drip or parison stretch, that's very hard to control if you don't know exactly what your melt flow is. And when you're using a lot of recycled content, the melt flow is going up and down. It varies all over. So melt flow control or parison stretch is very difficult to control. And what that means is these are on timers. So when we say, okay, time to extrude the parison, we want it to always be, say, 15 seconds to extrude that whole thing. If we do it in 15 seconds with one material, it's right at the bottom of the mold. When the mold closes, we don't have much of a tail, which is scrap that has to be reground. Whereas if it comes out very fast because melt flow is off, now you have a long tail and you have a lot of material. The interesting thing about when we add the micronized rubber to the pellet is that that parison stretch is very consistent. Don't know exactly why. We just know that the rubber seems uh, to balance out the parison as it's coming down. So it's a real advantage. One of the disadvantages is the material is it cools very quickly. So think of it this way: if it's 50% rubber, 50% plastic, the rubber's not melted. So all you're really cooling down is the plastic content. So there is some adjustments that need to be made in terms of how long you leave the part in the mold. Then compression molded or extruded parts. The pallets on the left were 50% rubber, 50% plastic. Again, we've created a plastic rubber pellet, run it through the extruder that goes to make these pallets, and we were able to get a very high content. Now, why would you want 50% rubber in a pallet? You probably don't, um, because it made the pallet very flexible. The idea was to show that we could make a very large part, like a 4x4 pallet, with a very high blend of material. This particular pallet had basically four injection points. Um, the way they made this, it wasn't truly a sprue or injector. They actually produced like a football of material and put it in the press. But the point is, you'd have four parts or four points of material going into this pallet, and it works very well. The material on the right is used for wraparounds of like posts or telephone poles. When they're in the ground, they'll wrap that around, and it helps to keep the wood post from getting degraded by the weather, ice, whatever, water. And that material had 70% in it. We were able to extrude 70% rubber, 30% polyethylene in that particular part. Kind of finishing up here, an example of a part here that is was previously a compression molded piece. It's a roof block. It's what if you have a flat roof and you're going to set air conditioners or piping, whatever, on top of a roof. This was a compression molded part that previously weighed about 5 pounds and had a break point of about 5,000 psi, or a load weight of about 5,000 psi. By converting it to an injection molded part, we were able to lighten the part to about 3 pounds. You can see on the back where we've corded out. What's hard to see in these photos is they were also able to put the logo of the company onto the part. And the part, not only did it reduce the weight of the part, but it also increased the break point by nearly twice as much, so up to 10,000 psi before this part broke. So again, the point of this particular application is we've taken a compression molded part, which is where you're mixing crumb rubber and urethane, putting it into a mold, compression it under heat and pressure for maybe as many as 15 minutes. Then you open the tool, dig the part out, you have a compression molded part. This part's able to be made in about 2.5 minutes. And when you make as this is a two cavity, what this did was one two cavity mold on a big injection molding machine was able to outproduce four compression molding stations that were making multiples of these. So big savings in labor, big savings in energy, big savings in material cost as well. Because the urethanes, for those that might be watching this that do compression molding and use urethanes, the urethanes, kind of like plastics, go up and down. So again, lots of opportunities, I think, in the compression molded parts world to be able to take compression molded parts such as this that are again from rubber and urethane and convert them over to an injection molded part. This is another example of a part using compression molding. On this one, what I put it in here, or I'm sorry, using injection molding, what I really wanted to show here is you can see some splay, what they call splay, and some surface imperfections on this part. It's important to note that that can all be adjusted out of the processing by way of additives into the plastic, into the compounded part pellets, and also by way of tooling technology. They have the ability now to heat or cool tools after the material's in. So even though this isn't a really from an injection molded standpoint a good looking part, I put it in there to show that you can make this go away. It's very very doable to get that part to look just as good as you want it. I wouldn't say a class A surface, but certainly a good surface. Some other examples of materials made with micronized rubber. Some of these, again, made by pellet, some of them with just a very low percentage in there. Some furniture, a lot of pots, a lot of vases. Here's some nice flooring that's made. And this is what's really exciting is the automotive guys are now starting to really take hold of this. They realize the value of the material and the quantity of chrome rubber that's out there. So when we start looking at all the plastic parts just within a car, for instance, on the right here, one wheel well liner, to put it in perspective, one wheel well liner on a car is typically about 4 pounds. And there's four wheels, so you have four wheel wells, 16 pounds of material. If that's made with 50% rubber, now you have 8 pounds of rubber going into each car. And of this particular car fender here, they make 300,000 of these cars a year. So that's 300,000 times eight. That's a lot of rubber, a lot of pounds of rubber. And there is, by the way, a material now spec through Ford. It's a Ford approved material that does have crumb rubber in it. And they're utilizing that material at Ford with more and more parts being produced every day from that material. Potential industrial uses. We look at things that's hopefully you can see these okay, but on the top left is a trailer. We're talking about floor mats for trailers, flooring, steps. Here you see some steps, whether they're into a trailer or a house that could be made. Manhole covers, speed bumps, all kinds of potential uses for these types of materials. So, in conclusion, the things I would just focus on is the scrap tire processing industry is obviously faced with some real challenges in what to do with all the rubber. Things like tire derived fuel, artificial turf infill, some of the real high volume materials we're finding challenges in those industries, both with the doing away of burning of the materials and the doing away with the rubber infills. The processing technology from our side, from the tire recycling side, has had a huge change, specifically with our Chrome Buster and the machines that are getting better and better at processing tires. We're able to produce very high volumes, up to 2,000 pounds an hour of 30 mesh rubber, which is a game changer in terms of micronized rubber costing. The pre-art compounds are improved by the lower material processing cost and the increased polymer performance. The PR compounds, sorry, I'm having a hard time seeing this here. There we go. PR compounds will not solve the enormous problem of scrap tires. Obviously, there's lots of challenges there. However, there is a place for these materials, and the use of them will grow more popular in the years to come as the plastic resins continue to rise, which they will, along with the price of oil. It's important to note that there are challenges that occur when using chrome rubber and plastics, such as surface finish, smell, dimensional stability, and others. But again, these can all be addressed through the use of additives, molding technology, advanced color concentrates, and other effective ways to transfer PR compounds into a material that is very standard or standard and similar, I should say, to a TPO or a TPE like material. Um, I do believe that the day will soon come when tire recycling industry and the plastics industry work together to embrace these new plastic rubber compounded materials. Uh, I believe that one day we'll wake up in the morning and realize the multitude of advantages that these materials have to offer, and will offer a wide variety of parts for which they can be used. So for many, it will be like Christmas morning, and that's a little tribute to my boss who came out of a molder friend of ours with an armful of parts, and I only let him keep one. So uh, that is the conclusion of my presentation. Thank you. And are there any questions?
Thank you very much, Bruce, for your presentation. We will start with a Q&A session. First question, when you say micronized rubber, which is the actual rubber dimension?
Uh, as I mentioned, it would be primarily there. People are using all different sizes. We believe the right size is a 30 to 50, at most 30 to 80 mesh. Anything below 30, and you start to get into a little bit too large rubber particle size, that when it gets into the extruder, the rubber tends to swell a little bit. And the screen sizes the screen packs that they use on the extruders to keep out contaminants are generally 20 mesh size screens. So we like to start at 30. It might swell to 25, but it's still, for those that don't know, the larger the number in mesh sizes, the smaller the particle. So even if it swells to a 25, it still passes through the 20 mesh screen. But primarily, we believe 30 to 50, 30 to 80 is the right size micronized rubber to use.
Thank you, Bruce. Next question. Is there any possibility of producing other colored products?
Absolutely. As I mentioned, the advancements in color technology allow us to both color the pellet in the compounding, in the twin compounding. We can introduce the concentrates there to create a colored pellet. Or there's been a lot of advances in post production or post processing, meaning that once the part's made, it can be colored via a paint or a coating.
Thank you, Bruce. Next question. What types of plastics can be used to create the plastic rubber pellets?
As I mentioned in the presentation, what we found with our testing is basically any olefin or propylene. Ideally, we've had extremely good success with polypropylenes. Polyethylenes, I've run LLDPE, which is linear low density polyethylene, all the way up to high molecular weight, high density polyethylene. There's a little bit of a challenge when you first dial those in, but once the formulations are done correctly, you can do those. But basically, the basic rule of thumb is any material that you can process under 400 degrees works very well. It's not going to work for polycarbonate. It's not going to work for nylon or any materials that you're processing in the high 400s to plus 500 degrees. Again, because at that point, you're charring the rubber because the rubber will not melt.
Thank you, Bruce. Next question. Apart from cost and ecological, which are the other reasons to use micronized rubber? Is interfacial adhesion with plastic good enough?
If I'm understanding the question correctly, you're saying why would you put rubber into something that if you can just make it out of plastics?
Mhm.
The easy answer is because of cost. When you're making, most of our clients that are making this type of 30 to 50 mesh rubber are able to produce it and sell it for roughly 15 cents a pound, $300 a ton US. Whereas I don't know of any plastics, scrap plastics, that are selling below 50 to 60 cents a pound currently, and I'm hearing numbers as high as 80 cents a pound for recycled plastic. So, the number one advantage is because of cost. Even when I didn't answer this, but it'll probably be a question, or didn't bring this up in the presentation. But the cost of doing the compounding is generally 10 to 15 cents per pound. So even when you add in the extra step of taking the micronized rubber, taking the recycled or virgin plastic or a mix thereof, and all the additives, then whatever that cost is material wise, you add 10 to 15 cents a pound for the cost of running the extruder. and pelletizing it, and it's still far below the balanced average price of the material is going to come in that 60 to 80 cent range, which is still below the virgin material in just a recycled, or I shouldn't say virgin, the recycled material in just a flake form or ground up form.
Thank you, Bruce. Next question. The end-of-life tires go through a number of your machines before they become powder. What is the lifespan of the blades? For example, how many times a year are they changed if the machines are running at full capacity?
So great question. It's a very varied answer in that if you can imagine if I'm a processor and I'm grinding up all the, let's say, scrap out of a tire manufacturing plant, um, those tires have never seen the road. They don't see dirt, they don't see wear, they're just, they're pretty fresh tires. So I'm not going to see a lot of contaminant. So let's and let me back up and say that each machine is different. The blades on the shredder are going to wear different than the blades on the grater, are going to wear different than the blades on the granulator. But the point is, the cleaner the tire and the cleaner the material going in, the longer the blades will last. So at EcoGreen, we have a specific sheet that shows how long our blades last for each one of our processes. But I can tell you on average, you're talking about thousands of tons on the shredder per year off of one set of blade. And again, this is going to vary by machine manufacturer, but with our blades, which are a triangle, you have three sides on one side of the blade. You can flip it over. You have three sides on the other side of the blade. So roughly 6,000 tons a year through that machine. Now, again, that's if the material is fairly clean. You're not running rocks through it, small propane tanks, things of that nature. If you're running the machine with just general car tires and truck tires, you're going to see that if you're running, the environment that you're running in. We have a plant that operates out of Saudi Arabia that has a lot of sand that gets in the tires. Obviously, the sand causes some issues in terms of wear. So it really depends on the environment and the types of tires, even so much as from passenger tire up to semi tire or OTR tire. But we can get specific information to you based on the types of tires that you're doing.
Thank you, Bruce. Next question. You discuss polyurethane as a material that can be mixed with rubber. Has there been applications of rubber and polyurethane for coatings?
Say the last part again, please, Augustina.
If
The
there
last
has been
sentence.
an application that combines rubber and polyurethane for coatings.
I am not aware of an application that's done if they're talking about coatings like in a twin extrusion system where you're extruding one material and then the plastic rubber over it. I'm not aware of one of those, but I don't see any reason why it couldn't be done. And the example I would use is, for instance, with like Trex, the guys that make the lumber decking, or I don't know if Trex does this specifically. I'm just using that as an example. Whereas a lot of single extrusion companies would extrude a single polymer for the product. Now they're using a base polymer, which I think this would work excellent in, where you could do like a plastic rubber mix, which would be a very low cost material for the volume of, again, using the Trex example of a lumber board. But then you could overlay or over extrude just a pure a high molecular weight, high density polyethylene over that. I think that would work just fine. Again, I haven't seen that application, but I don't know why that wouldn't work.
Thank you, Bruce. Next question. What is the minimum particle size you can reach with your equipment?
If by minimum they mean the smallest, we're able to produce 100 to 120 mesh in fairly good volumes. When I say fairly good, to me as a tire processing guy, I would say upwards of 500 to 1,000 pounds an hour. But on the size that we have identified for best use in this, that 30 to 50, our cracker mill is able to produce easily 1,500 to 2,000 pounds an hour of that material. And that is, by the way, that is not from a whole tire nugget. That's from the granulated material, which is typically 1/8 to 3/8 inches as a feedstock.
Thank you, Bruce. Would this new compound, this new material be recyclable again, and how?
Absolutely. Going through basically the same process of grinding. And when I say grinding, not in our equipment, in the plastic processors equipment. So the plastic processors that are using, general granulators with a whatever size screen they're using, 1/8 inch, 1/4 inch, 3/8 inch, they're able to do the same thing. It's just important to note that again, as they introduce the materials into their process, they need to know what the rubber content is. So if you were using say a 50% regrind of this material and you already have 50% rubber in it, and then you put our same 50/50 in as the virgin material, then technically your recycled content is more than 50%. So you may have some adjustments to make. The more you put recycled of this in, if you're using the same material on the infeed on the pellet form, then your percentages of recycled material content, or rubber I should say, are going to go up.
Thank you, Bruce. How much is the installed power on the crumb buster when they grind 2,000 pounds per hour?
Good question. So the motor that drives that is, I want to say, a 250 horse. But the nice thing about our cracker mill, what I really like about it, is unlike a gear driven box, ours is hydraulically driven with a Hagelin system, and we're able to achieve a wider variation of friction ratios, which gives us a lot more flexibility in how we process the material, and it also reduces the energy usage that we're seeing. So what does it use? It depends on the application, but again, we're basically running again, I want to say it's a 300 horsepower on that specific unit, but we're only running it at about 60% of capacity. So the hydraulic part of it really has a big advantage in terms of power consumption.
Thank you, Bruce. Have you done any testing on compound of plastic and EPDM rubber?
We have done testing. When you say of EPDM rubber, I'm assuming they mean our crumb rubber. So we've worked with companies such as Element Testing out of Detroit to do impact, IZOD testing, stretch testing for anybody that might be in the plastics industry watching us. You know how they make dog bones and they pull them apart. All that type of testing has been done on these materials, and we do have data that we can share with that.
Great. Thank you very much, Bruce. I would like to thank you for your presentation and for this Q&A session. And I would like to thank you all for taking part in this webinar.